Okay, let's dive right in. We're looking at this fascinating new frontier in robotics.
We really are.
We're talking about using these huge, um, hyper-realistic video generation models, like a VO3 or a 1 2.1, and basically turning them into instruction manuals for actual robots.
Right. But the big problem, the one everyone's trying to solve, is this thing called the embodiment gap.
Explain that a little.
Well, you can generate a perfect video of, say, a human hand opening an oven. The physics look plausible, everything seems right. But how do you translate that visual, that what into the precise joint movements for a robot arm? That's the gap.
You need some kind of a bridge, a middle language.
Exactly. And that's where this Dream2Flow framework comes in. It uses something called 3D object flow.
Okay, so the input is super simple, right? You get a picture with depth info, an RGBD image, and a command like open the toaster oven.
That's it.
But hold on, if the video that comes next is AI generated, I mean, it's not real. How can a robot trust that path? Seems like a shaky foundation.
That's the clever part. So an off-the-shelf video model generates a plausible clip. It just dreams up what success looks like.
Usually with a human hand doing the action.
Right. Then a whole suite of other AI models gets to work on that video. You got things like Cotractor 3, which is amazing at tracking points on an object.
And SAM2 for segmentation, for isolating the oven door from the rest of the scene.
Precisely. Those tools, combined with depth estimators, basically reconstruct the object's entire path through 3D space.
So you've just boiled this really complex robotics problem down to a tracking problem.
You've got it. The robot isn't figuring out how to open an oven from scratch. It's just following a pre-calculated 3D path. It's like a connect-the-dots puzzle.
And that lets it handle all sorts of different objects.
All sorts. The framework uses different planners depending on the task. For something like an oven door, it's a rigid grasp model, but for, say, covering a bowl with a deformable scarf.
Which is a nightmare for most robots.
A total nightmare. But here, it just tracks the 3D points of the scarf. It also works for pushing a block or putting fake bread in a bowl. It's incredibly versatile.
And that's why it performs so much better than the baselines mentioned in the source material, like AVDC and RigVid.
Yeah, those older methods just couldn't handle it. They sort of assume everything moves like a rigid block.
So as soon as you have a hinge or something that, deforms.
They break. They completely fell apart on the cover bowl task with the scarf. But because Dream2Flow tracks the point cloud, the actual 3D shape,
Yeah.
it's just so much more robust to those changes.
Okay, but for me, the real light bulb moment here isn't just the zero-shot planning. It's that this 3D flow can be used for something else.
Absolutely. This is the game changer.
It's a portable definition of success.
That's a great way to put it. You can take this extracted 3D object flow and just plug it in as a reward signal for reinforcement learning.
So instead of a human engineer spending weeks writing complex code to define the goal,
You just show it the flow. And policies trained this way are just as good as the hand-coded ones. And the best part, it transfers.
what do you mean it transfers?
The same flow policy can guide a Franca arm, a Spot quadruped from Boston Dynamics, or even a GR1 humanoid arm. It decouples the goal from the specific robot doing the work.
So wrapping up here, we've basically found a way around that embodiment gap. You can now do these complex, in-the-wild tasks, like the paper mentions sweeping pasta into a bin or pulling out a chair from a single text prompt.
It's an incredibly elegant solution for manipulation, but, and it's a huge but, it also outsources the biggest problem to the AI video model.
Meaning if the video model messes up, the robot is flying blind.
Completely blind. If the video model hallucinates an object that isn't there, or if it morphs something, which they saw in testing, a piece of bread turned into crackers mid-clip.
The robot's whole plan is useless.
The entire plan fails. If the AI's simulation of the world is flawed, the robot is doomed from the start.
So I guess that leaves us with a final question for you to think about. Is the biggest roadblock for future robotics not going to be motors or grippers, but the weird visual artifacts and hallucinations of the AIs that are supposed to be guiding them?